Hello, my name is Khalid AlHazmi, and I'm delighted to share with you our research on the autonomous operation of chemical reactors with reinforcement learning based economic model predictive control. Process control and optimization is instrumental to the operation of chemical plants. The goal for process optimization is to calculate the values of the process variables that lead to the best value according to a performance criterion. When the optimum values are calculated, process control aims to maintain the process at the desired operating conditions to ensure safety and profitability. However, disturbances, measurement uncertainties, and high-order dynamics in complex and highly integrated chemical processes pose a challenging control and optimization problem. The predominant paradigm in process systems engineering is model-based control and optimization. However, model parameters change over the operation cycle of chemical processes due to various causes, such as catalyst deactivation, equipment aging, feedstock variability, and more. To respond to such challenges, experts are needed to revise the process models, which is a slow and an expensive process. In our research, we seek to design AI-based algorithms with models that adapt to the changing characteristics of the environment to meet the requirements of future autonomous engineering systems. To achieve our goal of autonomous operation, we integrate economic model predictive control and reinforcement learning. Economic model predictive control is an online model-based calculation of optimal operating conditions with well-studied safety and stability guarantees. However, the performance of economic model predictive control depends on the model fidelity. On the other hand, reinforcement learning aims to find the sequence of inputs that drives a dynamical system to maximize some objective, beginning with a minimal knowledge of how the system responds to inputs. However, reinforcement learning, closed-loop stability, and process constraint enforcement are challenges that makes it less suitable for control tasks. In our work, we seek to leverage the safety and the stability aspects of economic MPC and the learning aspects of reinforcement learning. Here we present a framework for integrating economic model predictive control and reinforcement learning for online model parameter estimation of nonlinear systems. The economic MPC perceives the current state of the plant from the sensors and predicts the future state through the model. The controller takes the subsequent appropriate actions to optimize the closed-loop performance while meeting stability and input constraints. The reinforcement learning agent compares the measured states with the predicted states and modifies the model parameters accordingly. The main objective of the reinforcement learning agent in this framework is to learn a policy that responds to plant model mismatch caused by the continuously changing system parameters. This framework allows control, optimization, and model corrections to be performed online and continuously, making autonomous reactor operation more attainable. We have applied our framework to the oxidation of ethylene to ethylene oxide. This reaction resembles many industrial processes wherein a metal-based heterogeneous catalyst is used for a complex gas-solid reaction. In such environments, catalyst deactivation occurs and it is caused by various mechanisms such as sintering, poisoning, and buildup of deposits on the surface of the catalyst. This deactivation not only affects the catalytic activity and selectivity, but it also means that the kinetic model we started with is no longer accurate. Hence, model-based control and optimization will not be as effective. When the yield predicted by the model was compared with the yield of the plant when the economic MPC reinforcement learning scheme was employed, error in predicting the yield was less than 4%. In the figure on the left, we can see that employing reinforcement learning to update the underlying process model leads to a performance that is closer to the optimum than when eMPC is used alone. We can also see that as the catalyst deactivation increases and the deviation of the underlying model increases, the percent improvement over economic MPC alone increases as well. Thank you for listening, and please feel free to reach out to us for any questions.